So in this lecture, I want to look at reactions of imines, a little bit of a sidebar from the typical carbonyl chemistry, but imines are actually a lot like the other carbonyls that we're going to be studying. So let's get some imines in front of us now. If we recall that imines, let's make that smaller, sorry. Imines have a carbon-nitrogen double bond. The nitrogen has one other thing attached to it. Now, what I want to do is consider a resonance structure of an imine, and let's go ahead and put two other carbons on. We notice the nitrogen is electronegative. It's not as electronegative as oxygen, but we can consider a resonance structure where we've got charge separation, where the negative charge is on nitrogen, the positive charge is on carbon atom, which suggests that if we have a nucleophile, we can add to the imine, and that is indeed the case. We can add a fair number of nucleophiles to imines, just like we can with normal carbonyls, which gives us a range of types of products that we can form. In particular, we can form new amines, in this case, secondary amines. Now, while we could add a whole slew of nucleophiles if we wanted to, in this class, we're going to stick to kind of being aware of mostly one, sort of two. Okay, so the first one I want to mention is the hydride. And I'll just get these in front of us. The ones we're going to worry about are hydride, and that'll be from NaBH4 and lithium aluminum hydride, LAALH4, LiAlH4. Okay, and then there's also Grignard reagents. So let's look at the hydride nucleophile really quick. So hydride addition to imines. Now it turns out that this is not too different from what we would expect. If we recall what hydrides can do, they add to carbon-oxygen double bonds to make alcohols, for example. Here we're adding to carbon-nitrogen double bonds to result in only single bonds, and that gives rise to the functional group amines. Remember, amines are our starting materials that we react with carbonyls to give imines. So let's consider our imine. We're going to mix that with either sodium borohydride or lithium aluminum hydride. And we're going to basically add an H minus followed by some H plus workup will give us a structure where we've added two hydrogens to our carbon-nitrogen double bond, resulting in an amine with an A. Now we have just single bonds on the nitrogen atom, all from carbon atoms. Again, the rules about, no carbonyls attached to nitrogen still apply. So if we have two hydrogens that are being added, the first one, which I'm highlighting in green, comes from the hydride donor. The second one comes from the mild H plus workup. And this is pretty mild H plus workup. We don't really have that strong of an acid being added, but I'm not going to go into that right now. Okay. So this is the reaction. We could look at the mechanism of it, but it's fairly similar to the mechanism we've seen before for sodium borohydride and lithium aluminum hydride reductions, where what we do is we consider that charge separated resonance structure that allows us to see how things are going to add. That puts a positive charge on the carbon atom and a negative charge on the nitrogen. We're then going to add to our hydride donor. In this case, I'm going to choose the BH4 anion, and I'm just going to show the negatively charged hydride adding to the nitrogen. I'm not going to worry about the boron complexing to the nitrogen, though it indeed does, at least to a certain extent. I mean, it does, yeah. Okay, so we're going to add that hydrogen to our nitrogen atom, still considering this negatively charged, again, it's probably bound to the boron, activating it for subsequent hydride donations if we need it. And then from here, we're going to have our H plus, and this H plus is from the workup, like it's added at the end of the reaction to clean everything up. The negative is going to attack the positive, and we've got our product formed. So our mechanism is now complete and we formed the product. So that's it. That's kind of the reaction of imines with hydrides. Now, it doesn't seem like a big deal, but it actually allows us to take advantage of a super useful process called reductive amination. So reductive amination is the reason why I want to talk about this, the reason why I've kind of organized this lecture in this way. So reductive amination is a synthesis of amines with an A from carbonyls. And this is going to involve a two-step procedure. So using a two-step protocol that looks like this. In step 1, we're going to react the carbonyl with an amine to form an imine. Okay, so we've seen that reaction before. I think that was the last lecture, or at least close to it. This is where we're going to take an amine or something like it, something that's primary with an NH2 on it, and we're going to do a condensation reaction where we mix the two together and release water as a byproduct and swap out the oxygen of our carbonyl for nitrogen to make an imine. So we do have to start with an amine, but we're going to make a more complicated amine after we do the second step. So that's step 1. Now in step 2, we're going to add a hydride reducing agent to convert the imine into an amine. Now what that looks like is we're going to take our imine, shown here, we're going to react it with NaBH4 to make our amine. Now this amine is more complicated than what we started with because we've added additional carbon units. Okay, so this is a really important way to make amines, more complicated amines, using carbonyl compounds. So it's a two-step procedure looking at two steps that we've already seen. So what we want to do is kind of merge these things together, the formation of imines with the reduction of imines to make cool amines. Okay, so what we want to be able to do is predict the products. For if we had carbonyl plus some amine, let's go ahead and throw a benzene on here. We're going to do step 1, we're going to mix those two together. That's going to be our condensation reaction. In step 2, we're going to add NaBH4, okay, or we could write then NaBH4, implying that's what's last. And at the end of this all, step 3, we're going to have H plus workup. So in step 1, we're going to mix the carbonyl and the amine together to make the imine. Step 2, we're going to reduce those. In step 3, we're going to work everything up. That's going to give rise to a product where now the oxygen is swiped with nitrogen, and the nitrogen gets what it had originally. So this is going to be the overall product, and we can't forget that the nitrogen atom is going to have a hydrogen now from the reduction step. So that's reductive amination. And it allows for the synthesis of complex amines through the intermediacy of imines. So we're going to use imines as an intermediate to make complex amines. Okay, so super important chemical process. Now the next thing I want to mention is the reaction of Grignard reagents with imines. So this is going to be really the Grignard reaction of imines. Now let's recall what the Grignard reaction is. What you do is you take a carbonyl and you add it to some carbon group that's attached to magnesium bromide. The outcome of this is you form a new carbon-carbon bond where the carbonyl position now adds to the R group. The oxygen now has a hydrogen. So we can't forget we need some H plus workup in here as well, some dilute acid. So this is an organic 1 reaction. It's probably one of the most important reactions we learned in organic 1. I mean, it's not as important, I guess, as the fundamental substitution reactions and elimination reactions. But it's a really powerful reaction, something hopefully we took with us from organic 1. But many people need a review. So quick review. What you do is you first make the Grignard reagent. The Grignard reagent is unique in that it has the atom magnesium in it, but it's not made from difficult things. That is, we're typically taking a haloalkane, some R attached to bromine, for example. We're going to mix that with magnesium in the zero oxidation state, and the magnesium is going to slide between the carbon and the bromine bond. Okay, now what's cool about this is when we start, the carbon atom is delta plus. It's partially positively charged because it's bound to an electronegative element, the bromine. After we engage magnesium, now we're going to be delta minus. Why is that? Well, the magnesium is actually a metal. So we're actually bonding to a metal now, which is way on the opposite side of the periodic table, and so is highly electropositive. So as much covalent character as we want to give this bond, let's recognize that it's highly polarized this time towards carbon, which means we're going to have negative character on that carbon. In fact, when I think of a Grignard reagent, I find it most helpful to just sort of cross the magnesium out and replace the R group with a negative charge. That's because Grignard reagents behave like, that's a person, Grignard reagents react like carbanions. So they act like carbanions, which means they're mostly negative. Mostly C minus. Now that's a simplification, if I'm honest, simplifying a few details, but it really does the job for us, and I find it to be quite helpful. Okay, so if that's the case, when we're trying to picture the mechanism for a process that looks like this, what we can do is simplify things. Let's get all these details out in front of us. We can simplify things by first considering a resonance structure of the carbonyl where we have a negative charge on the oxygen and a positive charge on the carbon. We can then cross out, this isn't a resonance structure, we can cross out the magnesium bromide and just consider an R minus instead. The R minus can then engage the carbon with a positive charge to give rise to a species with a new carbon-carbon bond. The oxygen is still negative, but that's where H plus comes in from the workup step. Oxygen grabs the H plus to give rise to the product. Okay, so that's the Grignard reaction. Maybe it's a little bit easier to see than it was in organic 1 because now we can consider, or at least get more comfortable with these charge separated resonance structures. Okay, now with that in mind, let's go ahead. I don't mean to get that off the page too early. Let's consider the reaction of imines with Grignard reagents. Okay, what I want to do is again consider a charge separated resonance structure, but let's first get the products in front of us. Okay, so I guess to finish that thought, there's my charge separated resonance structure. Okay, so we're going to have our imine. I'm going to put an R prime just to show the two R groups are different. But we're going to react these things together under the same sorts of conditions to give rise to whoops, I screwed that up. H on the nitrogen, R prime on the carbon. It's basically the Grignard reaction again. We just have a different pi bond that we're adding to. Okay, so if I consider the charge separated resonance structure, I could clean this up a bit, where we've got nitrogen with a negative charge and then carbon with a positive charge. And we again consider the Grignard reagent as being in a carbanion, an R with a negative charge. We can see the negative charge will be attracted to the positive, the carbon atom, to give rise to, go all the way over here, a species where we now have a carbon bond to the R position. And we have a negative charge on nitrogen, which just reacts with the H plus in the workup step to give rise to the product. Okay, so there's a few examples of reactions of imines with nucleophiles. And the two nucleophiles we want to worry about with imines are going to be hydride, that's a very powerful reductive amination, and then Grignard, which gives unique amines by way of carbon-carbon bond addition. Okay, so two important reactions of those imine molecules that we made last time. And now going forward, we'll zip back to typical carbonyls with oxygens and that sort of thing. So until then, see you next time.